In this video, we will continue our discussion of trigonometric substitutions. So as a recap, if your integrand contains one of these three expressions, that is an indication that we can try a trigonometric substitution. And then after you apply the trigonometric substitution, you would apply one of the corresponding trigonometric identities. So we're going to finish up by just looking at a few more additional examples. So let's evaluate the given integral. Now note it doesn't contain a square root of x squared plus 4. Here it's raised to the 3/2 power, but it's really just having this expression x squared plus 4, which indicates a trigonometric substitution. So the x squared plus 4 indicates that the trigonometric substitution that we would want to use is x equals 2 tangent of theta, so that dx is going to become 2 secant squared of theta. And what we need to do is take the original integral only involving the variable x and write it solely in terms of thetas. So x squared plus 4 is going to become 4 tangent squared theta plus 4. That's raised to the 3/2. And then the dx is 2 secant squared theta d theta. Once we have applied the trigonometric substitution, we look at that term and we see a corresponding trigonometric identity we can use. Tangent squared plus 1 is secant squared. So we can rewrite the denominator as 1 over, this will be 4 secant squared raised to the 3/2 power times 2 secant squared theta d theta. And then we just go ahead and we simplify accordingly. So if we have 4 raised to the 3/2 power, the square root of 4 is 2, 2 cubed is 8. So the 4 pulls out as an 8, but you have a 2 above it. So we end up with a 1/4 out front. If you take secant squared and raise it to the 3/2 power, the 2's cancel, and you have a secant cubed in the bottom. So this becomes secant squared all over secant cubed. And secant squared over secant cubed is simply cosine. So this is 1/4 the antiderivative of cosine, and the antiderivative of cosine is sine. So in this case, that resulting trigonometric integral turned out to be very reasonable. And what we need to do at this point is rewrite in terms of that original variable x. As we saw in our previous video, in order to do so, we take our trigonometric substitution and we use that to draw a corresponding right triangle. So we have x over 2 is equal to tangent of theta. So for our right triangle, we'll label the theta. Tangent of theta is x over 2. And to determine the length of this remaining hypotenuse, we use the Pythagorean Theorem. So the square root of x squared plus 4. And as we noted earlier, this x squared plus 4, which appears under the square root, is exactly the term in our original integral which prompted this trig substitution. So looking at our triangle, sine of theta is equal to x over the square root of x squared plus 4. So put back in terms of the original variable, 1/4 times x divided by the square root of x squared plus 4, all plus c. Let's now look at a similar type of example, but in this case, one with a definite integral. So once again, identifying this x squared minus 4, that is an indication of a trig substitution. The trig substitution which this indicates is that we should use x is equal to 2 secant of theta, which makes dx 2 secant theta tangent of theta d theta. So we need to take our integral solely involving x's and rewrite it so that it only involves the variable theta. So x squared minus 4, so this is going to be the square root of 4 secant squared theta minus 4, divided by x, which is 2 secant theta, multiplied by dx, which is 2 secant theta tangent of theta d theta. And at this point, the procedure is identical to the previous one. We can even note an obvious simplification. 2 secant theta on the top, 2 secant theta on the bottom. But at this point, we also need to note that it is a definite integral, which we started with. We've used a substitution, which means we need to change those limits of integration. So let's change those limits of integration. So for the lower limit of integration, when x is equal to 2, that means what? 2 is equal to 2 secant theta. So secant of theta is 1. And remember, secant is 1 over cosine. So cosine theta equals 1. So here we're thinking specifically in terms of 0 to 2 pi. That would imply that theta is equal to 0. So our lower limit of integration is 0. Similarly, for that upper limit of integration, when x is 4, we're going to have 4 is equal to 2 secant theta, which is equivalent to saying that cosine of theta is equal to 1/2, thinking between 0 and 2 pi. That would tell us that theta is equal to pi over 3. So as an upside, even though we had to go through this process of changing the limits of integration, what that means is later on in the problem we will not need to resubstitute, which means a right triangle is not going to be necessary. So let's go ahead and continue our evaluation. So the square root of 4 secant squared theta minus 4. That's 4 times tangent squared. And the square root of 4 tangent squared is going to be 2 tangent theta. So we have the integral from 0 to pi over 3. So that becomes 2 tangent of theta, something that will hopefully become quicker and efficient as you do more examples, multiplied by the remaining tangent. So the 2 pulls out front, and we have the definite integral from 0 to pi over 3 of tangent squared. Now looking back to our techniques we used for evaluating trigonometric integrals, what we have is an even power of tangent and no secants present. So what we need to do is rewrite this tangent squared in terms of secants via the Pythagorean identity. So this would be 2 times the integral from 0 to pi over 3, and tangent squared is secant squared minus 1. And now that we've rewritten in terms of secant squared, this is an antiderivative we can evaluate just term by term. The antiderivative of secant squared is tangent of theta, and the antiderivative of 1 is just theta. And I've gone ahead and distributed through the 2. And now, using the fundamental theorem of calculus, we plug in pi over 3. So we're going to have 2 tangent pi over 3 minus 2 pi over 3. And then we subtract away what we get when we plug in 0. But note, tangent of 0 is 0, and then we're subtracting away 2 times 0. So what we are left with is 2 tangents of pi over 3, and tangent of pi over 3 is square root 3, minus 2 pi over 3. So note, from a procedural standpoint, when it is a trigonometric substitution in a definite integral, we do need to change our limits of integration. So kind of a downside there, we have to think a bit in terms of trig functions. But the associated upside is at the end of the problem we do not need to resubstitute. Once we've anti-differentiated, we then use the fundamental theorem of calculus. Let's investigate one more example involving a trigonometric substitution. This is a common example. Upon inspection, we cannot immediately apply, at least in this form, a trigonometric substitution. But what we can do in this situation is first apply an algebraic technique, one that we all really enjoy. We can complete the square. So let's do just a little bit of algebra to the side. If you have x squared plus 2x plus 26, looking at the coefficient of x, which is a 2, x squared plus 2x would be the first two terms of x plus 1 quantity squared. So thinking about completing the square, I'm going to rewrite this as x squared plus 2x plus 1 plus 25. So this becomes x plus 1 quantity squared plus 5 squared. So if we go ahead and just replace that term in the square root in the denominator and write this as 1 over the square root of x plus 1 quantity squared plus 5 squared. Now this is something that looks like it could be solved very efficiently using a trigonometric substitution. We are going to take the x plus 1 and we are going to set it equal to 5 tangent of theta. And note that this is equivalent to saying that x is equal to minus 1 plus 5 tangent theta. So that dx is 5 secant squared theta d theta. So putting everything in terms of thetas, the x plus 1 is going to become 5 tangent theta. So we have the square root of 5 squared tangent squared theta plus 1, and the dx in this case is 5 secant squared theta d theta. And this works out very conveniently. So note the tangent squared theta plus 1 in the denominator is really secant squared of theta. So our integrand, we are going to have a 5 secant squared theta in the numerator. And in the denominator, we have the square root of 5 squared secant squared, which is 5 secant theta. So algebraically, the 5's cancel off, and the square of the secant and the secant in the bottom cancel. And what we are left with is the antiderivative of secant of theta. And if you go back to our first video where we introduced common antiderivatives, something we mentioned is that the antiderivative of secant is something that does appear frequently, and it's a trigonometric integral. The value of its antiderivative here will be the natural log of the absolute value of secant theta plus tangent theta. And it is recommended that this is an integral that you should make sure to commit to memory in case you see it again in the future. So lastly, we need to draw an associated right triangle to get back in terms of that original variable. So looking at our substitution, we have x plus 1 over 5 is equal to tangent of theta, and we have an associated right triangle. So theta, x plus 1, 5. So by the Pythagorean Theorem, the hypotenuse should be labeled as the square root of x plus 1 squared plus 25. And once again, make the observation that x plus 1 squared plus 25, corresponding to the side we had to label, is exactly what prompted the original trigonometric substitution. So putting back in terms of x, we see by inspection that secant of theta would be the square root of x plus 1 squared plus 25 divided by 5 plus tangent of theta, which is x plus 1 over 5 plus c. So one last big picture observation. Before applying a trigonometric substitution, it is very reasonable that you would first have to do maybe some algebraic manipulation, in this case completing the square, or start off by using some other method of integration.